All right, I guess we should just get started. Okay, so finally, after some delay, we have new versions of HSDS and h5pyd out. I've actually talked about many of these features in previous Call of Doctors, so go to your YouTube archive and you can dive into any of these. If not, if there's something particular that is of interest, we can talk about now, or you can post to the forum or whatever. Anyway, I guess briefly, uh, of these new features, I think hyperchunks is this idea to support mapping to HDF files that have rather small chunk sizes, which is pretty common. And the problem with that is it's inefficient for HSDS to map to lots of small chunks. So what hyperchunks does, it kind of virtualizes chunks into larger groupings, so it's more efficient. Multi-link and multi-attribute methods. This is like an efficiency to create multiple links or attributes in one call. We have bit shuffle compression, support for fixed width HDF8 strings, which is a rather peculiar HDF5 library feature. Dataset shapes can be reduced now, and broadcast operations where you say write 5 elements and it gets blown up to 500 or whatever. And h5pyd, we have these new examples: NumPy 2.0 support, fancy selection, swimmer compatibility, again, the multidimensional hyperchunks, and multi-manager, which lets you parallelize dataset reads and writes. And I think all these features we've talked about on previous Call of Doctors. Okay, any questions about the new releases? Okay. Again, if you later on, if there's any kind of questions you have, feel free to contact me in the forum or elsewhere. Next, I'd like to show an example. I think last time in Call of Doctor, we talked about Swimmer, the single writer, multiple reader applications. And that's something that's supported, I'll bet, slightly differently in both HSDS and HDF5 library. But today, I want to talk about a multi-writer, multi-reader application, member, I guess. And that's something that is only possible through HSDS. So let's go to this example. This is actually checked in to h5pyd under examples. I don't know what this is here. MWMR underscore multiprocess.py in examples. So let me walk through this code briefly. So starting in main, we have these options for dataset count, process count, attribute count, and SN count. So let me go through each of these. The application will create dataset count datasets, a new file. And it'll use, optionally, process count processes to do that. And in each dataset, it will create attribute count attributes. And then finally, SN count is how many HSDS endpoints will be used. And we'll get into details of all these options as we go in. But basically, we come here, we create a bunch of dataset names, and we parse these names out into this process count groups. So each writer will have a set of datasets to create. And for each dataset, each writer will create attribute count attributes. So if I say create 4 datasets with 10 attributes each, you'll have a total of 40 attributes created. And then I use this Python multi-process package for managing the multiprocessing aspect. And it's actually fairly easy to use if you haven't done it before. I always feel somehow we have these modern computers with so many cores, but we use Python code that is basically limited to one core. And it's not too much extra work to be able to utilize all this amazing processing power we have. So there's this class called h5pyd, and it takes an endpoint, a file name, a set of data set names, and the attribute count. And this is a class defined here. And we go here and we have a list of writers. And then we say writer.start for each writer. And we keep track of our writers with writers.append. So this is a list of these processes. And then we wait here. So this writer.join says, wait until that writer is finished, and then continue. So after we loop through each of these writers and I've done a writer.join, everything's done as far as all our subprocesses, and we just print the finish time. And we can close the file. So let's look at the writer class, which is up here. So h5pyd. We take this endpoint, file name, dataset names, attribute count, and it's pretty basic. We create this h5pyd.file in append mode. So meaning we're not going to initialize a new file, and we're not only read-only, we're going to be modifying the file. And then for each of these data names, we create a bunch of attributes, and then we're done. Okay, so let's see how this works. So if I do, let's see, so .h will show you these options again. And let's verify our HSDS is up. So HSDS is running, and we have 4 nodes, and we're new h5pyd version. So if I do this, okay, I'm going to create a domain under test user 1 called mwmr.h5, and I'm going to create 200, is that right? Yeah, 200 data sets and 4 processes and 100 attributes. So we'll have a total of 20,000 attributes created. So let me do it with just one process first. And this will take a while. So we have one process and 100 attributes. And let's see how long this takes. Maybe that was overambitious. Let me put this down to 50. Okay. So 50 data sets and 100 attributes. So we created 5,000 attributes, and it took 22 seconds. Now, what's the advantage of all this complicated multiprocessing code? If we go here and say use 4 processes instead of 1, it should run faster. So we had 22 seconds with 1 process, and basically 5 times faster, right? With 4 times faster with 4 processes. And so from 22 to 5, and if I say create, if 4 was good, maybe 8's better. Let's try that. Okay, so here's the complicated thing. This actually took longer, right? So why is that? Well, let me run this again. And at the same time, I'll have this window. So if I do Docker PS, I see I have these my Docker containers running, right? We have there's basically one SN container, 4 DN containers, and a head container. And if I do Docker stats, it'll show you how busy each container is. So now we have our 4 DNs, or 1 SN, or 1 head, and they're all basically idle at this point, less than 1% CPU. So we run this again. And sorry, I didn't look at this. So now we see the DN containers are like 20% CPU, but the SN container was 100% CPU. So that's the problem, right? As we create more sub-processes, all these processes are writing to this one endpoint. Hey, so how long was I talking to myself?
Not any more than like a total gone time, maybe 20 seconds.
Oh, okay. Yeah, okay. You guys need to toss out some random comments periodically, so I know you're all still there.
Don't forget
Anyway,
to share.
so I was showing Docker stats, and you'll see that, let me just repeat in case I was talking to myself. When we run this 8 processes, and we go to Docker stats, you'll see my DN containers are using a moderate amount of CPU, but the SN container is pretty busy. Let me try that again with a longer runtime.
Hey, John, we don't see your screen again.
Oh, shit.
Great. I have to get a buzzer to buzz that out.
Okay, share screen.
Okay, yep.
Okay, so Docker stats, and we'll run this example. And what we're seeing here is that our SN container is 100% CPU, right? So we have these 8 processes. They're all talking to this one SN endpoint. And even though the SN endpoint is relaying work to these DNs, because there's only one SN container, that becomes overloaded. And therefore, that limits the amount of potential increase we can have with more than one process. Okay, and it might be a good time to show this our kind of diagram of the HSDS, where we're having 4 SN containers and 4 DN containers talking to the object store, right? Well, by default, when you run HSDS in Docker on your desktop, you only get 1 SN container. But you can actually have options to run any number of data node containers, any number of service node containers. So let's do something to make it more like this actual diagram. So let me stop our current HSDS. And then if you do, you'll see that we actually have options for a number of data node containers and number of SN no containers. So by default, this is 4 and 1. But if I do, say, 4 and 4, you'll see now we have a total of 9 containers. And so here you have SNs 1, 2, 3, and 4, and data nodes 1, 2, 3, and 4, and the head container. Okay. Now, each of these SNs has a different port number. So if I do, say, curl HTTP localhost 5101 about, this is sending a request to SN1, or maybe SN2, it doesn't matter. But then port 5102 would be the other SN container, and 5103, and so on, right? So you have these 4 SNs all looking at a different port. And to take advantage of these multiple SNs, you need to specify the endpoint that your process will be talking to. So that's, if we go back to the code now, you'll see there's this endpoint option. And in the main, we say host is localhost, base port is 5101. And when we're firing up the subprocesses, we say use port, base port, plus our number of SN nodes, the process modulo the number of SN nodes, and that becomes our endpoint. So if we have SN to be 4, now we are talking to 4 different endpoints. If we have, say, 8 processes, you'll have, say, 2 processes talking to one endpoint, 2 processes talking to a second endpoint, and so on. Okay, so let's see how this works in practice. So go back to our example. If we keep the default 1 SN, like it says, and then if we do Docker stats, so like before, we have these 4 SNs, but only 1 got targeted. Here, let me do that again. So you see here, this SN3 apparently is attached to port 5101, and it got all the requests. And these other SN guys are idle because no one was talking to that port number. And this took 9.8 seconds. So let's use 4, since we have 4 SNs. And then go to our Docker stats. And now, happy case, we see all the containers using a reasonable amount of CPU. Right, so we're taking advantage of each of these cores that we have running on our computer. And strangely, that took longer. Let me try this again. So if we have, let me try 50. So now we're going back to using 1 SN container. That took 9 seconds. And if I use 4 containers, not as much improvement as I thought. Let me try this. So we use 16 processes with 4 containers. And 6.3 seconds. This is a little different than I was seeing earlier. I think maybe running Zoom causes a little more use on on the laptop than otherwise. You kind of see here, if we run this in the system monitor, you see as I'm running it, we spike up to almost using 100% of our available cores and then back down again. So it's a bit of a black art, I have to say, that these parameters you use for a number of processes and the number of containers you run, it all will depend a lot on the particular application you are using. So I think this ISCA approach, though, is to have these things like the number of processes be parameters. And then once you have your code working, you can experiment with what actually works best for a particular application on a particular computer system, and so on. And as always, if you need help with this, we are here. So write to info@HDF Group or post on forum, and we'll be happy to convince your particular problem. All right, that's all I have for today. Any other questions?
John, just a quick question. This is made available because of the multi-processing Python variant you're taking advantage of. But correct me, this has always been a possibility using the vol connector, but we could always use multi-read.
Well, it's a little complicated actually, because
I think we lost John again.
I think that was a little more complicated.
Yeah, it's always hard to tell if he's thinking or if he is.
I didn't realize it was that complicated of a question. Perhaps I underestimated.
Hey, John, he's back in, although we see you frozen. Okay.
hey, I'm back. Okay. Yeah. So Robert was asking a question about doing this kind of thing from using the vol connector. And unfortunately, there's a bit of a problem, because even though you can have a multi-process, well, I take that back, right? So multi-threading, there's a problem, because even though your application is multi-threaded, and even though HSDS can handle simultaneous requests, the actual library is kind of like having two interstates connected by a single lane country road, right? So library enforces that only one thread can do something at any single time. So that's this locking. So even though it's supportive of multi-threading, it's not actually concurrent multi-threading, right? So that limits your approach for multi-threading. But multi-process, I think that should be fine, because each process is totally independent. Now, you wouldn't want to try writing to an HDF5 file using multiprocessing. Very bad things will happen. But with HSDS, the HSDS service is handling conflicts where you're, say, trying to add attributes to the same data set from different processes and so on, right? So it handles the concurrency part. So I actually haven't done that, but I think that should see reasonable usage of multiple cores having a multi-process C application using the RESTful connector.
Okay, but a multi-threading is going to be rate limited by that
right.
thread
Now,
access.
there's work in progress to resolve that. So we can hope for the future, but I think that's still out of ways.
Okay, but when that problem is solved, HSDS will be completely compatible with that. It'll be ready to go.
And I wouldn't say that. I think there'll need to be some updates to the REST-valve connector itself as well.
I see. Okay. Okay.
I think.
Okay.
But that should be relatively straightforward to do. Right. But till then, you should be able to take advantage of multiprocessing. Now the complication of multiprocessing is that it makes it harder to share data among your processes, right? Because in multi-threading, all your threads share the same memory space. It's easier to coordinate your threads. With multiprocessing, if you need to communicate between your processes, you'll need some kind of IPC method to do that.
Yes, there's a lot more work on that end. Yes, nothing comes for free there.
Yes, right.
Yeah.
Right.
Okay,
Yeah.
thank you.
So, Robert, if you try some experiments, we'd like to hear back on how that goes.
All right, it's not on my immediate list of things to do, but I will keep it in mind. Thank you.
Okay. All right. Great. Okay. Well, I should say goodbye before my Zoom connection fails again. But it's been great, and we'll catch you next time.
All right. Thanks, John. Bye, everyone.
Bye.